We finished up last time with skew and kurtosis, is that correct? Ish? Come on, is that where we ended up? Okay. And we talked about why we're not interested in necessarily statistical tests of skew and kurtosis. Ignacio, we had talked about this, so you brought this up at one point, like, oh, well, you know, we've got these different tests to see whether or not we have significant skew or kurtosis. I would make the argument, different opinions in different fields, I would make the argument that I really don't care about that, because my assumption of my test isn't that skew is 0, that kurtosis is 0. What I'm more interested in is the shape of the data, and so the absolute deviation from normality. If things start to get really, really non-normal, then we start to worry about stuff in some situations, but other times we might not worry about it at all, depending on what type of analyses that we're doing. Again, our general rule of thumb for acceptable deviations from normality, skew or kurtosis values under 2. This doesn't mean that skew or kurtosis values under 2 means that data are approximating normality or close to normality. You look at the data with a skew value of 1.2 or 1.8, you very clearly see it's not normal. But we're starting to get worried about then if they start to exceed that. Kurtosis can start to get a little bit bigger. So the main concern there is that we're going to underestimate with either positive or negative kurtosis. They're underestimating population variance. But even if we have positive kurtosis, after we get a sample of about 100, that starts to become not worrisome. Above 200, the negative kurtosis. What's negative kurtosis? Kind of flat, boxy, right? So the positive kurtosis is kind of that peaked. So about 100, 200. Again, these are rough guidelines, right? But recognizing that most of our data are fairly most of our analysis is going to be pretty robust to kurtosis, skew-ish. So looking at absolute values more so than getting concerned with whether or not something's different from 0. Questions on this? All right. And again, histograms, box plots are a good way to go through and take a look at normality. Kind of a little asterisk here, recognizing that histograms look a lot different depending on how you set up those histograms. I can jimmy a histogram and make it look like a lot of different things depending on how to work the binning. SPSS kind of does this automatically for you. Stata will, but you can kind of play around with some stuff. So one, just be careful with when you look at those histograms. All right, so again, for a group-based analysis, when we're talking about normality, again, we've talked about this before. With group-based analyses, our concern is with the distribution of the sample means, not the observed distribution, right? So in situations where we have decent cell sizes, about 25. Now, 25 per cell is not a large design, but it's sort of starting to get to situations where we start to get fairly robust, even if our data are looking pretty wonky, okay? So that's good. But the thing that we need to be thinking about is, under what circumstances are our analyses not robust, right? And again, this is a review from last semester. Remember that if I have distributions across cells that have different shapes and also different variances, then I start to question whether or not my analysis is going to be robust, right? So if I have condition 1 has like a pretty intense positive skew, condition 2 has a pretty intense negative skew, and I have evidence of a violation of homogeneity of variance there, then I start to worry about whether or not my omnibus tests are going to be on point. I have different sample sizes and different variances, right? This was something we talked about quite a bit last semester. If I've got 20 people in this group and 200 in the other group, and I have different variances, all of a sudden then I start to get worried about that mean squared error, right? Because remember, the mean squared error in your ANOVA table is just like a pooled error variance for the whole design, right? And that error term is what's going to get used for the calculation of all our standard errors, okay? But if that pooled variance is my larger sample, the sample of the cell that has 200 people has a larger variance, I'm going to have too conservative a test. I'm going to overestimate variability. If the larger sample has the smaller, I'm worried about that I've underestimated the total variability across the cells, and now I have too liberal a test, right? So again, if I've got wildly unbalanced design and clear evidence of violation of homogeneity or variance, then that starts to become problematic. If I did have small sample sizes and violations of normality, I've got 10 to 15 people per cell and crazy distributions, that's problematic, right? So what we see with our group-based analyses, normality is less of a concern than for regression in some of our continuous evaluation of continuous models. But when we start doubling down on violations, right, unbalanced designs, unequal variances, skew in different directions and things like that, that's when we start to get worked up about stuff. Questions about any of this? Yes.
So looking at multiple variables, I get that like skew in opposite directions is problematic. Like what broadly is like the approach if you have several and they have, I guess, like fairly problematic skew for the sample size, but they're all, you know, all positive. And maybe you have like something else going on as well.
And again, so the number one thing is if I have reasonable sized cells, that makes me pretty robust to stuff, right? If I have different variances, but everything's kind of positively skewed, I think about substance use stuff. A lot of the stuff you look at is just all positive skew, as long as it's not too crazy, right? And basically what you're asking is are the number of people I have in this cell or this group, is it enough to handle having some extreme values, right? My big concern, and with your means-based analyses is, okay, so I have some extreme values. What's the likelihood that that case or those set of cases are going to start dragging that mean out, right? Thinking about how likely is it going to start to sort of drag that mean around? Because if I have 100 people, I can have one squirrely person way the hell out there and it's not going to do anything, right? But if I have 10, 15 people, and oftentimes when we're doing psychopathology research, that's what we have. Now all of a sudden I'm worried about that person who's a heavy cannabis user or something like that, starts making the mean not representative of actually what's going on with that sample. That guy's just dragging things out, right? And so in that situation, this is where, and we'll see today, we can go through and do some transforms. Transforms don't always make things look pretty, but they at least bring things in line to something that's probably a little more acceptable in terms of analysis. Okay, that help?
Yeah.
Yeah, Sean.
So on the bottom one, what if we have reason to believe that the population is normally distributed?
That what?
The population is normally distributed, but our sample may, or just because it's small, we can't really tell.
So you're saying, sort of whatever I'm looking at has a normal distribution of the population. I just happen to get a weird sample that.
Or the sample's so small you can't really tell if it's normal or not.
Yeah. I mean, if that's the situation, then all of a sudden you've got probably bigger issues than the distribution of your stuff. Then we start to worry about if you actually have enough people to say anything meaningful about your data, right? With the small sample sizes, reading probably what's, if I've got a small sample, I'm not worried about necessarily about my kurtosis. I'm probably more worried about, well, I am, and that if I got really positive kurtosis, that means I've probably underestimated the variability within that cell, and it's going to mean I have too liberal of tests because my standard errors are going to be too small. So I have a little bit of concern with that, but probably the more thing I'm more concerned about is, do I have enough people to actually power the...
It's more on the small sample size.
Yeah. So basically I'm running a test that will fail to detect anything outside of massive effect sizes, and then we start to question whether or not it's useful to do it. Other questions about this? This is one of the things that sort of gets people sort of really worked up about stuff. I think actually the error that people probably make, at least in social sciences, is over-identifying problems as opposed to under-identifying problems. But always want to go through and think carefully about what's the potential impact of this stuff. All right, outliers. Outliers. I actually don't like the word outliers. Outliers, people say outliers like it's a definitive thing, right? Like, oh, this is an outlier that everybody agrees on. Highly, highly subjective. I like to use extreme values, because that seems, I don't know, semantics, it sounds better to me. But we're we're talking about a univariate outlier. This is going to be extreme value in some individual variable. Multivariate outlier, this is going to be represented as an atypical configuration of scores among your, generally among your predictors when we're talking about regression, okay? So let's say I'm running some type of model where I'm interested in predictors being age, income, and region, some sort of geographical code or something like that, right? And so I can have someone who's 10 years of age, right? Is someone who's 10, is that a univariate outlier? No, there are 10-year-olds in the world, so that's not shocking, right? What about someone $130,000? That's within the normal distribution of income. That's fine, I'm not shocked by that. I've got someone who lives in the rural South. People live in the rural South. That's not a weird thing, right? But if I put all those people together, now all of a sudden I've got a case that's quite strange, right? If I have a 10-year-old residing in the world South with making $130,000 a year, that's a strange case, right? So individually, none of these characteristics are weird. But if I put them all together, now all of a sudden I've got a problem. I've got a case that can start to have a massive impact on sort of my estimations and things like that in a way that's not terribly predictable. Okay. I don't know. I need to update my. I mean, this is starting to get. This was funny in like 2013, and now.
I think it's coming back.
You think like just go old school, like bring it back to 2013?
Well, also like the 10-year-olds residing in the rural South are just not making money like they used to. Nobody to update it.
Like that. It was too bad. Like, oh no, this is all the 10-year-olds in the rural South. They're making money. Okay, so thinking about outlier, and this starts to become important. Like, what's causing an outlier or an extreme value to be an extreme value? Obviously, incorrect data entry. If someone's sort of made an error in terms of entry, if I have entered 999 for missing data code in SPSS and failed to tell SPSS that 999 is missing data code, it's going to register it as an actual value, and you're going to get weird graphs and things like that. Also, a good reason to go through and look at those graphically. Case member is not case is not a member of the intended population of study. Okay, this starts to become important. He's going through and taking a look and saying, is this person someone who I'm actually interested in looking at, right? So Chris, let's say you're looking at exercise in college populations or something along those lines, and weight and things like that, right? And so you've measured hours of weekly exercise, and now all of a sudden you get someone who's reporting 20 hours a week of exercise, right? What might be going on with that case?
I mean, 20 hours seems like it would be outside of the normal range.
Yeah. And so what situation might someone be exercising 20 hours a week?
Perhaps if they have an eating disorder.
If they have an eating disorder, sure.
If they're an
What
athlete.
else? If they're not have an eating disorder, what's that?
If they're an athlete.
If they're an athlete, right? So what I've done is I've gone through in my sample, I've captured someone who's a student athlete. They're a basketball player, they're a swimmer, wrestler, volleyball player, something like that, and they've just got a lot of practice hours, right? And so what I might say is like, okay, this person isn't actually, college athletics isn't part of what I'm wanting to look at. So yes, this person is an outlier, but they're an outlier because they're not a part of my intended population of study. And so I can get rid of that person without any concern about impact on my stuff, right? Or let's say, again, I'm looking at income of college students, and I get a college student with reporting an income of $150,000 a year or something like that, right? That might be, say, a business person taking MBA coursework, something like that. Like, okay, what I'm interested in is 18 to 20-year-olds and sort of that type of thing. This is someone who's in their 50s, who's an established professional, who's taking a class. So this person is not part of who I'm looking at, right? So thinking about this. But we can have situations where a case may be a member of the intended population, but my population variability is underestimating my sample. Right? So Nick's doing research on, what's your substance of choice, Nick? Cannabis. Like weed. So you're going through and taking, and so you're going through, but marijuana is illegal in the university, or in the state of Wyoming, right? And probably, I would imagine, cannabis use in the general student population is fairly low-ish, okay.
State, I guess.
From his, okay, right? But maybe he goes to and finds someone who's smoking several times a day, right? But your sample is maybe only 50 people, right? Your 50 people is probably underestimating variability in cannabis use, right? And so you've got someone who isn't, like, probably are doing this study to capture people who are heavy users like this. But this person ends up being an outlier because if, say, the population distribution of what I'm looking at looks something like that. Is that fair? Yeah. Okay. Correct. No, that's terrible. But what my sample looks like is something like this, and then that person's out there, right? Well, then that means like this person is part of my population. They're not weird within the whole distribution of things, but it's just I, in my sample of 50, captured just that, which makes sense because that's where most people are going to fall. And then I just bingoed one person way out there. Now I have to decide, what am I going to do with that? How am I going to go through and treat this? Do I want to get rid of that person? Probably not, because they're an important piece. This is probably maybe the one person in my sample who has very clear clinical issues with maybe a cannabis use disorder. I don't want to get rid of them, but I have to think about how I'm going to go through and address that. Questions? Okay. So, possible consequences of our outliers, undue influence on our coefficients. So we start to get bias there. Inflation of type 1, type 2 errors, reduced generalizability of the solution, right? A lot of this is mitigated by having reasonably large samples. But if I'm working with smaller samples, which is what we're often dealing with, that outlier can start to have a pretty big impact on stuff. So identifying, right? One thing we want to think about, we don't often think about this, is outliers in dichotomous variables, right? So I've got 0, 1 binary code for something. I have something that have largely uneven splits, 9 to 1. You can think about it as a case of an outlier within a context of a yes/no variable, okay? And the problem is we've got cases in the smaller category. If I'm, say, CJ's, or say Nick is looking at methamphetamine use or something like that, right? And you've got, and this would be pretty generous, right? 90% of my sample is not methamphetamine, but then 10% are meth users. That's a weird thing, but let's say let's say it's 95 or not even 5%. That's probably still huge, but I still want to look at that, right? That 5% has a far, far bigger impact within that group than the 95 people in the non-user group, right? And so we've got individuals. It's Wyoming in the U.S. Senate, right? We've got 500,000 people, but we're having undue influence with our 2 Senate representatives relative to California, who has 1 billion people, and they still get 2 representatives, right? That's kind of the same thing that's going on here, right? So the characteristics of anybody in that tiny sample start to have a pretty big impact on your overall solution. We get attenuation of associations. If we have very, very small versus very, very large groups, and I'm looking at associations with continuous variables, starts to make those correlations look smaller than they probably should be. And if we're in a situation where I'm looking at a variable, and let's say like I've got a split, right? And I'm like, oh, I thought it would be kind of interesting to take a look at this, but it's not a central part of my analysis. It's not central to my question. What I'd probably do is start thinking about maybe omitting that, just so I don't introduce difficulties into my solution. Questions about thinking about outliers within the context of dichotomous variables? Okay. Continuous variables, we can talk about this as having extreme standardized scores. Again, 3.29, that's associated with the z-score p equals 0.001. I mean, anything that's, if you look at 3 standard deviations above or below the mean, we're talking about 0.1%. Beyond that, in the tails, that's pretty extreme, right? So we can start to think about how we're gonna, to remember is not to get too excited about this and to get too cut crazy, because if I've got a large sample, I'm for sure gonna have people out there in the tails. It's almost certain, right, that I'm gonna have some extreme scores. If I didn't, that'd be sort of strange, right? Particularly, again, any of you in clinical work, if I've got a big clinical sample, I would expect some people to be out there on the extremes, right? So I'm not gonna get too worried about it. And if I've got a large sample, if I've got someone who's pretty far out there, that might just mean they're pretty far out there. They may not necessarily have a huge impact on my solution, right? So this is, as we're going through and we're doing screenings, needing to take a lot of stuff into consideration in terms of what are we gonna, okay, identifying something above or below a threshold is one thing. That's the easy part. It's what's the impact, how do we deal with it in a reasonable solution, okay? Other thing we've got going on for us in psychology in general, our scales are semi-arbitrary with kind of a cap, right? You can only be so far out, right? Again, I think just income is just a good example. People can have crazy, crazy high income. There's no, the sky's the limit on your income, right? And so we can get stuff like that starts to drag, or like home prices or things like that start to drag things way out of bounds, right? For the type of thing we do, it's generally a cap on how high you can be, but still wanting to think carefully. If we do identify a case, what's going on with that case? How do we deal with it? So, identifying outliers, box plots. We worked with box plots. You all know and love box plots. Box plots are nice because box plots follow a set of rules that histograms don't. I can screw around with my histogram, make it look like a lot of different things, right? Box plots follow a set of rules that make all box plots look sort of more or less giving us the same information. So midline is our median, right? Remember that box plots are median-based, graphing out median-based statistics. Bounds of the box. This is my first and my third quartile. Sally, can you tell me what my first and third quartile is?
First and third quartile are your minimum and maximum values, right?
Okay, not the minimum maximum. What's Q1 and Q3? What's that?
The median.
Okay, median. Okay, yep, you're close. Median's in the middle. Median is Q2. That's your second quartile. Someone help us out. What's the first and third quartile?
25 and 75%.
What's that?
25 and 75%.
Yeah, the 25th percentile, the 75th percentile. So this, assuming a normal distribution, well, not assuming it's sort of normal distribution, just sort of the data that there are. 25% of scores will fall below the first quartile. 25% of scores will fall above the third quartile. And in between, this is your interquartile range, right? Anybody remember what we can also call the interquartile range? Your middle 50, right? Middle 50. This 50% is half of your scores in your distribution are falling between your third quartile and your first quartile, right? Middle 50, that's half of your scores falling here. Okay? Your whiskers, okay? Whiskers are a little bit tricky. These can be a couple of different things, right? They can be your minimum or your maximum values, right? So in this case, the whiskers represent my max value, my minimum value. Right? CJ, how do I know that these values correspond to my max and my min values?
There's nothing past them.
Yep, there's nothing past them. There's no data points past those two, right? So in this graph, we're seeing that the whiskers represent the most extreme, the largest value in the set, and the smallest value in the set. Okay? Chris, what would this look like if these didn't represent the min and the max value?
They would be represented by individual dots. If
Yeah.
in SPSS, they would have the case number.
Yeah.
If they were outside.
Yeah, if we tell SPSS to do it, right? What we start to see is whenever we start to see values hanging outside of that, that means that that these whiskers represent the maximum value in the set that still remains within 1.5 times the interquartile range. So if I take the interquartile range and I go 1.5 times outside the interquartile range, if I've got values beyond that, the whiskers represent sort of the last value that still remains. This is the last value we hit before things sort of went off the charts and things get beyond 1.5 times the interquartile range. Our outliers were extreme values. These are going to be individual points extending beyond the whiskers. For SPSS, anything plus or minus 3 times the interquartile range going to be represented by asterisks, right? Now, whether or not, and if we've got data that have relatively normal distribution, we're generally assuming that about 95% of the data fall into those two whiskers, okay? Now remember, do extreme values, things that are even 3 times the interquartile range, do those have to be like light years away from the rest of the distribution? No, why not, Chris?
Sometimes your distribution needs to be really tight.
Yep.
So
Yep.
I can just get a little bit outside of it.
Yeah, and particularly when we have plots where maybe we've got what does that suggest?
Your median and your first quartile and last quartile are all the same.
Yeah, they're all the same
They're
value.
yeah.
Right. And so, what type of distribution is this displaying?
Which is it? Positive.
Yeah, this would be an intense positive skew, right? My first, my third, my second quartile, all at the same exact value. And so if anything is, what's 3 times the interquartile of 0?
0.
Anything that's not on that value, right? And so what's nice with these is we can start to sort of get a sense for kind of what's going on with our data. So box plots are a review. Any questions? Feel comfortable with this? Okay, cool. So how do we address our multivariate or our univariate outliers? We've made an entry, we fix the entry. If the data are problematic, and this is important just from a method standpoint, right? If I'm going through, so either you're running a study, want to keep, and it's an experimental lab-based experiment or something like that, right? Want to keep good notes because if you could have someone who's squirrely and looking weird, right? If you've taken good notes, or your research assistants are taking good notes, you might be able to go back through, take a look at the record and say, oh, this person wasn't paying attention, or this person was on their phone the whole time, or this person finished up with a set of questionnaires in 2 minutes when it usually takes people 15 minutes, right? And then you can say, okay, this is someone who wasn't taking the protocol seriously. I can throw them out with any concern there, okay? Case isn't representative of population of interest. You can get rid of that person, right? But sometimes, and this is for you guys, have you done stuff in other classes in other areas, talking about like censored means and things like that? Yeah, right. Do you feel comfortable telling? Do you know what's going on with that?
No, maybe.
Okay.
Censored means?
Censored means and censored sort of variables and things like that. Basically.
So it's at the extreme where if they could have said that it was higher, they would have.
Oh yeah, that would be a censored variable. Yeah, that's a little bit different thing. If I go through and I say, okay, what I'm going to do, and this is common practice for addressing this, and you'll see this in some areas where we go through and we say, what I'm going to do is I'm going to cut the top 15% off all the top 15% of scores. I'm going to get rid of those. Bottom 15% of scores or 10% of scores, let's say 10%. So I'm going to take top 10%, get rid of that. Bottom 10%, get rid of that. And so what I'm working with is just kind of the middle of the distribution, right? There are areas where that's a common practice, just because we're expecting things to be super, super low, super, super high, and so we're just going to work with the middle, right? Which is fine. Problem is that now I've just lost 20% of my data if I've cut the top 10% off and the bottom 10% off. I'm working with 80% of my sample just right off the bat. And if you're in psychological sciences, I'm sort of worried about my sample size anyway. I can't just go losing people just because, right? And so in thinking about how do we do this, particularly when we're working with samples that we're worried about power anyway, right? Smoothing procedures, This is going to be replacing the outlying score with a value 1 to the next largest, right? So what we're doing here is we're maintaining rank order, right? So let's say, Ignacio, you're working with a study and you've got 3 cases that are all quite extreme, right? What you might do is you might decide to say, hey, everything else is looking pretty good. I don't necessarily want to transform and lose interpretability. What I'm going to do is I'm going to take these 3 values. If I can make the argument that what I'm going to do is I'm going to take the one that's the least extreme, butt that up and to bring that person into the next score in the distribution. The second most extreme, put it next to that. Third most extreme, put it next to that. So they go rank order 1, 2, 3, sort of the same out, right? Again, we're keeping those people in the same position as they would have been. We're just reducing sort of the variability and the ability of those cases to start dragging my mean out, okay? So that would be a smoothing procedure, or what we can do is we can change the shape, right? We can go through and we can transform. Transformation has its place, and it's in some areas it starts to become expected, right? So substance use is an area within experimental psychology. If I'm doing reaction time stuff, reaction time always going to have a positive skew. Most people are going to be pretty quick, but then people are going to get slower and slower and slower. You don't have anybody who's like superhuman and like you've done it like a billionth of a second, right? The skew is always going off into one direction. And so if we're using reaction time scores, it would be strange to see someone analyzing reaction time scores without some sort of transform, right? So you'll see this start to become pretty common within some areas, and within some areas, the log transform of something is just something we all know, and so it's actually fine. Like, it's not really losing interpretation because we just use it all the time, so I can say, oh, well, that's a pretty big log transform or not, right? But with most of the stuff that we're doing, particularly if we're using variables that have some sort of intrinsic meaning, right? So if marketing stuff like that, if you guys were working with income, right? The log transform of income is much more difficult to understand than dollars, right? And now all of a sudden that becomes a problem, right? Weight, right? Weight, I know what weight is. I know that sort of how much more 200 pounds is than 150 pounds, right? And so if I start screwing that around, it starts to lose some interpretation stuff, right? Like number of occurrences or uses, that makes some sense to me, but then log transform, that's just the nature of the data, so we all do it, right? And so less concern there. But what we don't want to do, what I would argue against, is save the transformations until they're necessary, and not just do it to do it and then pretend that we didn't do it, because then that starts to impact the interpretation stuff. All right. Important distributional issues. Make sure that we're going through, and if you've got a distribution that needs something to happen to it, make sure you do that before you roll into multivariate outliers. Because otherwise, if I've got a wonky distribution, and then I look at, and I don't do anything with it, and then look at multivariate outliers, what am I going to get? A whole hell boatload of multivariate outliers. They're going to be all over the place, right? Save yourself some time. Address the univariate stuff first before you go through and start looking at multivariate outliers. All right. Transformation. People love transformation. People transform something at the drop of a hat. When we start to have problems with conceptual issues and how we go through and interpret stuff, right? And a lot of this can be broken down, thinking about data-driven versus theory-driven analyses. Someone had asked me about hierarchical or stepwise regression models. Who would ask me about stepwise regression models? So this is like basically entry, so we're entering variables in the model if they reach a certain threshold, and sort of then sort of moving forward with that.
Give up the class.
Give up the class, yeah. Anyway, that would be an example of a data-driven model, right? In this situation, right, I have no a priori assumptions about what's going to be the best predictor. What I'm interested in is for these data, right, for this model, I'm interested in maximizing my ability to predict my outcome. And so I could care less what variables are in here, right? If it predicts in this set, it's going to go in, right? And there are a lot of fields that are sort of definitely a data-driven type of approach. In psychological science, that's rarely the case, right? When it's a more theory-driven analysis where I've got variables in the model because I think those variables are important. Now, whether or not they turn up in the sample, I don't know. That's why we do the study, right? But conceptually, I can make an argument that it's important for this variable to be in there, so the variable is going to be in there from a theoretical standpoint, right? And if this is the type of thing I'm interested in, then all of a sudden, if I'm just looking at the association between x and y, but then I go through and I transform y, now all of a sudden I'm not looking at the relation between x and y, I'm looking at the relation between x and the log transform of y. Log transform of y is a completely different variable than y, right? I impose a nonlinear transform that changes the shape and makes it more amenable to analyses. But the problem is my outcome is no longer the outcome that I wanted to look at, it's a different outcome, and I need to deal with that and think about how I'm going to go through and communicate that, right? So it starts to become incumbent on me if I've gone through and I transform a variable that I need to communicate that in my write-up to my readers so that they know I'm not looking at dollars anymore. Like the outcome is not dollars, right? This is not sort of the expected increase in dollars giving you an increase or decrease in whatever. It's the log transform of dollars, which is a different situation, right? And so wanting to go through and have some sort of, at least in psychological science, wanting to have some sort of strong justification for transforming a variable before we just go through and transform things just for the hey-ho heck of it. So again, the batch of Fidel saying, okay, go ahead and transform. I'm sort of less pumped on it. I've sort of grown warmer to the idea of transformation. The problem is this is one of those things that starts to become overused, right? People just transform without having a good reason for transforming. And the problem is in terms of complication of interpretation or pretending I didn't do it when I did and then just charging ahead with that. Questions about why I'm at least encouraging you to be careful about sort of decisions to transform. Yeah.
What about in the instance where you have a repeated measure, and it's like a linear change that you're expecting? Is percent change or percent difference an appropriate variable to compute and then analyze, or is that?
Yeah, that starts to become tricky, and there are certain types of transforms, and we'll get to that in a moment, where log transform to gap transform is kind of nice because within the context of a regression model, that still retains interpretive value, and so that's good. But if I was, let's say, in a repeated measures ANOVA, right? And this was kind of if you remember the treatment data that we looked at, the inpatient stuff, right?
Yeah, so for that.
Right, so as it started to started out pretty normal, right? And then our outcome as we moved along, by the time we had billions of people in there, so it wasn't, but started to get more skewed, right? And the concern would be like, oh, do I then go through and transform that last time point because it looks problematic? Don't do that, because then all of a sudden your repeated measure is not the same thing. If you take the mean of the log transform of your variable, that's going to be a completely different value than the means of the other. And so it starts to become not consistent. Same thing, people do that sometimes, like, oh, I'm doing measure development and I have 20 indicators that I've written, but some of them were skewed, and so I'm going to go through and transform some of them, but not other of them. That's not good, right? So for those types of analyses where you have something that should be all on the same metric, if you elect to transform one of them, you probably transform all of them, and then kind of see what that looks like. But then again, like thinking very carefully about what are the assumptions of my tests, right? For repeated measures, I would say it's a means-based analysis, right? My concern with the distribution of sample means, and so even if this is looking, even if I have some time points that are kind of have some violations of normality, do I have enough people to make my analysis robust to that? And then what I'm worried about is for those assessments of those time points that are more, have some skew or something along those lines, is it enough to start seriously making a difference in terms of sort of the mean values?
Right. I guess I was asking about the magnitude of change from time 1 to time 2 using a newly computed variable like percent change from like taking all of the change overall, and then from time 1 to time 2, and then from time 2 to time 3, if that was.
Yeah, that starts to get in, and then there's some concern with using change variables in terms of the reliability of like a change variable. Like sometimes it doesn't make a difference, right? Because mean change in the standard deviation, and you start to get into other stuff, it starts to become a little bit different, and so that starts becoming more sort of kind of a tricky question. But at any point when we're thinking about using any type of, or analyzing any type of transform variable, what we're doing now is we're now shifting away from a comparison of mean values into a comparison of median values, and we're going to talk about kind of why that works. So in terms of transformations that are common, you see these transformations can look like anything. If I'm a statistician and I'm doing like regression diagnostics, we can get into some pretty creative transforms, right? But if you're going to transform, it's like, I don't know, it's not the same variable anyway, so go nuts, right? Now there are some that we'll talk about, like the natural log ends up being nice because it retains some interpretive value. But thinking about moderate positive skew, square root of x, large positive skew, natural log, large positive skew, but my variable has 0 values. The natural log of my variable plus some constant. Okay? Why do I need to add a constant? Yeah.
Because some values are 0.
Yeah. And what happens if I try and take the natural log of 0?
You don't get anything.
I don't get anything. It's a problem, right? So if I have a 0, because if you just tell SPSS to do it, it'll do it. It just won't give you a value for anything that's 0, right? So you have to keep an eye on that. Severe positive skew, you can use an inverse transform. So 1 divided by x, that kind of flips things around. So you got to be careful there. You got an L-shaped distribution, something that's like sort of super skewed. Again, an inverse with a constant. Again, I can't take 1 divided by 0. That's not going to give me anything, right? With negative skew, now all of a sudden we've got things going the other way. If I just if I just use a natural log transformation for a negative skew, it's going to make that a lot worse. And so what I need to do is I need to reflect that. And so what we do, if I've got a negative skew, what I might do is I might take the square root of some constant minus x, right? And a constant is going to be some value that I subtract from each score so that my smallest value is equal to 1. So k is usually the largest score in the distribution plus 1. So if my largest distribution, I've got a 1 to 100 scale, right? But it's going to a huge negative skew. So most of my values are 100. What I'm going to do is I'm going to take the square root of 101 minus whatever my x is. So that all my people that are 100, what's their new value in their reflected variable? 1, right? So it swoops it all around, and my person who is 101 minus 1, 100, right? So when we're working with negative skew, in order to transform this, what does this mean in terms of interpretation?
Kind of the opposite of what you'd expect.
Yeah. Down's up, up's down, right? Very, very, very important that you recognize that and keep that in mind, because otherwise all your stuff's going to look like it's backwards, right? And maybe you get excited about that and then misinterpret it like, well, you just used a reflected transform, right? So needing to be careful about that. So same thing with large negative skew, the natural log of a reflected variable, severe negative skew, or the inverse transform of the reflected variable. So actually with your reflection, if you go 1 over, you use a reflective transform or the inverse transform, the inverse transform here, that's going to flip your scale around too, right? Because again, 0 to 100, 1 divided by 100, what's that? Tiny number. 1 divided by 1, that's a big number, right? So if you use this inverse transform, it's going to flip your scale around all the way anyway, right? So wanting to keep in mind and make sure that you're understanding what's going on with these transforms as you go through and apply these. And these are just some, there's lots and lots of other ones. These are ones just to match up the infidel layout that are fairly common. Questions about this? So again, I hinted at this with my ungrouped data, okay? So this is going to be the stuff like for regression and things along these lines. I'm interpreting my associations as associated with my effects, my coefficients, as associations with the untransformed variable, or with the transformed variable. So I'm looking at the association of extroversion and the log of aggression, okay? I can't interpret it as aggression. It's not aggression, it's the log of aggression. It's a different thing. If I'm in working with group data, my differences are now not looking at mean differences across group A and group B. I'm not looking at differences in the mean of aggression across boys and girls with ADHD. What I'm now looking at is the difference in medians between groups, okay? With our nonlinear transforms, when I transform, it's going to change the shape of the distribution, okay? Chris, if I z-score, if I run a z-score transform, or if I turn all my data into z-scores, does it change the shape of the distribution? No. It's a linear transform, it's fine. It's just sort of, the shape is the same, right? If I have a weird distribution of my observed variables and create z-scores, we should have a weird distribution, right? With our nonlinear transforms, the whole idea is to change the shape of the distribution. The shape of the distribution is problematic, right? And so it's going to change the shape, but it's not going to change the order of the scores, okay? Whoever's at the median is going to be at the median. The median of the raw data is going to be at the median of the transform data. Whoever's the max is going to be at the max. And the transform variable, same thing as they were as the untransformed variable. The person who's second from the bottom is still going to be second from the bottom in the transform variable, just like they were in the untransformed variable. The transform is just going to shift things around. Okay. So this is a graph I stole off the interwebs, right? So here's my untransformed data, right? Here's sort of the score, or sort of distribution. Doesn't look too bad. But let's say that, like, this is the median, right? Let's pretend, okay? And so let's say I am at this value here, right? I'm still going to be at the median value here in the transform data. My position, my rank relative to everybody else doesn't change, okay? So when we're talking about differences in scores, group level differences, we're looking at differences functionally in the median values if we've got a transform variable with our group level analyses. Give him credit, this is polyandrous live-bearing fish. This is more interesting than stuff I do. So.
What is that?
Oh, it's just, this was the article that I pulled this from. Evans and Gasparini.
Only, okay.
Seminal article, right?
Something in the fish.
All right, multivariate outliers. Okay, so we talked about univariate outliers. How are we going to go through and address this? Multivariate outliers change how we go through and talk about these a little bit and how we identify them. But one of the statistics we can use to identify multivariate outliers is by looking at leverage. Okay, leverage value is going to reflect or be a measure of distance of some case from the centroid of the remaining sample. Okay, now this starts to get into some geometry type of thing, but all you need to know for your purposes is that a centroid is the intersection of the means of all predictors in the analysis. Okay, all right, so we're going to do some geometry again. Thumbs up, XY axis, XY axis. Okay, we've got extroversion and aggression. Extroversion on the x-axis, aggression on the y-axis. We see my mean of extroversion here, my mean of aggression here. So at this point right here on the x-y axis, this is my centroid, right? Now let's go through and say, go in three-dimensional space, right? And so now I've got the mean of extroversion, the mean of, you need to participate in the activity. Thank you. mean of extroversion, mean of aggression, and then let's say impulsivity, right? That makes some sense. Now impulsivity is another predictor. Now all of a sudden we're talking about some point here in three-dimensional space is my centroid, right? As we start to get into 4 predictors and things, then it starts to get crazy and we can't think about that in sort of geometry terms. But what we're looking at is within the group of predictors, where do the values, the combination of values for this case lie relative to the mean of all others? Okay. So if we've got, let's say, we're looking at in 2-dimensional space, we're looking at the association of height and weight. Okay, and so here is the centroid. So we've got people who, on average, about 68 inches, 180. I don't know if that's sort of right, but let's just say that is right. And so here we've got the centroid, so the mean of the sample, and then here we have someone who is 6 foot tall, or 60 inches tall, and 220 pounds. What makes this a multivariate outlier? Yeah.
Because typically weight and height correspond with one another. So the fact that this individual is 60 inches and then 240 pounds is...
Yeah. So this is someone who's actually not very tall, but actually is quite heavy in terms of sort of relative to the height, right? And so this person is existing sort of outside of sort of what would be expected. Is 60 inches a univariate outlier? No, probably not, right? Is 220 pounds a univariate outlier? Probably not, right? We've got perhaps sort of more extreme values in opposite directions, and when we put those together, then we start to get something that looks like a case that's not consistent with sort of the other things. What if we have a third variable? Okay, let's say we have someone who's 76 inches tall. Okay. We got someone who's 6'4", someone who weighs 230 pounds, or did maybe at the start of their career. Is that a strange person? It's a big person, right? What if we add sex? What turns that into a for sure multivariate outlier? Yeah, I mean, that would be large for a man. It would be sort of very, very large, a very, very large female, right? So maybe this person's plays for WNBA or something like that, right? But this is kind of maybe, oh, this is kind of an extreme value, but it's kind of an extreme value that's kind of going on the same line. But as soon as we add a third variable in there, now we've got someone whose stature is not representative of their gender, right? And so now all of a sudden we've got something that's turned into an obvious multivariate outlier here. Okay. People kind of get the idea of multivariate outliers, kind of what's going on and how they can pop up in our set. So when we find a multivariate outlier, number one thing we need to do, so identifying it is fine, whatever, that's easy. We just plug the right things into our statistical package and say, oh, that thing looks like it's a multivariate outlier, right? What we want to do then is determine why that's statistically deviant, okay? Our leverage won't tell us why it's odd. It's just will tell us that it, relative to everybody else, it looks to be different. What we then need to do is want to go through and make a determination of what's actually going on with that case, right? Is this someone who we want to keep in the analyses, make decisions from there, okay? This is a very, very important part. Once we identify these, going through and pulling and wanting to say what's caused this variable to be an outlier, one, it's going to help us identify variables that are problematic and make decisions on whether or not we should or shouldn't retain this, and then also giving us a sense for what type of people might not this solution generalize to, right? So we want to know why, before we pitch anybody, what specific values or variables are causing this case to be distinct from the rest of the sample. And then we can make a determination on whether or not what we want to do with it. But then the other thing too is so I've got a regression model that does a very good job of looking at the relation between exercise and weight for university students, right? But what I might say is when I see that I got a couple of student athletes in there, I might say this model doesn't generalize well to student athletes. So this model works if I'm talking about your run-of-the-mill average university student. Where this model isn't going to work if we start into sort of getting into people who are engaged in a considerable deal of exercise for the purpose of competitive sports. Now all of a sudden, this thing that might indicate eating pathology within sort of the normal sample actually does a pretty poor job of predicting eating pathology within this other sample, right? And so thinking about in terms of generalization, so where does my model fit and where does it not fit, right? From a trauma-based perspective, right? I might go through and I might find that I'm sort of looking at sort of trauma stuff and academic performance or something along those lines, but then all of a sudden I get a constellation of survivors who are maybe older and sort of have distinct characteristics. What I might find is that these are student veterans who have come in who are sort of at a different stage and sort of doing different things, and I might say, okay, this model does a good job of accounting for academic difficulties in students in general, sort of exposed to civilian trauma. But then I've got a group of people who are looking a little bit different in some way, and so this is maybe not going to be a good model for them. That's important things to know in terms of research and sort of how we're moving forward with stuff. Questions? Okay. What we can do is we can use some regression techniques to go through. We basically hijack regression to get a sense for what variables in my model are creating, causing that case to be a multivariate outlier. Sometimes we can just eyeball it and see, but sometimes it's nice so you can, particularly if I've got a number of different predictors, have some sort of analysis, some sort of procedure to go through and figure out exactly what's happening with that stuff. Okay. So addressing these, right? What we want to do first is take a look and identify the number of magnitude of cases that are being flagged as potential multivariate outliers, okay? We've got rules of thumb, and I'm going to give you rules of thumb to use, but those rules of thumb are no good, okay? What those rules of thumb are going to do is they're going to over-identify problematic cases. And so if you just cut off people because they exceed some sort of threshold, you're going to be losing a lot of your sample, and it's going to be hard to justify that, okay? And if I just start excluding people because they don't fit specifically in the perfect normal distribution, what I need to do is I'm going to get a big reduction in my sample size, and I'm potentially going to lose potential generalization, particularly for certain types of things that we're looking at. We may be interested in people who are sort of more out on those extremes, and if I get rid of those, now all of a sudden my model just pertains to people who are right there in the middle of the distribution, which may be fine, but maybe it's not, because maybe the middle of the distribution doesn't represent the people I'm actually interested in, right? So we need to be careful there. Other thing we want to do, and this whole approach that we're going to take, the big debate within the statistics community on how to go about testing and screening for regression analyses and things like that. Some people will make an argument that, you know, using residuals and sort of doing some of this stuff, that all this needs to be done before you run your model, because if you're doing it after the fact, then it's just futzing around with stuff, and you have potential to throw people out that sort of make your data do what you want it to do, okay? Which is kind of the principled approach. In real life, so we can sometimes find people who we leave in, leave out, and sort of thinking about the impact on the model is actually quite large. So their decisions can start to have a pretty big impact on what our actual model looks like, right? If I have any one person in a reasonably sized sample that starts to have a massive impact on sort of what my results look like, should I have that person in my model? No, right? If one person is driving all of the effects that I'm getting, and if I get rid of that person, everything else falls apart, that's a warning sign. That's not good, right? Because what I've probably done is I've probably ran an analysis, ran a study that's never going to generalize anything. No one's ever going to be able to replicate, because Siley was the only reason I got the weird effect that I wanted to find and made a big deal about it. But my study is the only study Siley's ever going to be in the entire universe, right? And so when CJ tries to replicate 7,000 times, Sally's not in that study, and so it's going to crash and burn, right? And so going through and identifying, so going through and taking a look at the same cases, all right, here's 2 or 3 cases that I think are potentially problematic from the standpoint of my analyses. I don't know. I've got my eye on these folks, right? And so what I'm going to do is I'm going to go through and run this. You don't want to drop all 3. That's not good, because then who knows what that's going to do, right? We'll run a series of models successively, dropping them from the analyses, right? And if it doesn't change the model functionally, what should I probably, well, I don't know, what might you do? Keep them in there, right? That keeps me from having to make an argument for why I start pitching people out. Anytime you start pitching people out, you're going to have to make a strong argument for why you did it, and make that compelling so that it doesn't sound like, oh, this person didn't do what I wanted them to do, so I just got rid of them, right? So if they don't have an impact, you can go through and say, identify cases, however these cases had no functional impact on the results of the overall model, therefore we kept them in, right? That's easy. But if they do, right, then you have to go through and say, hey, so we found cases high influence, high leverage, problematic with multivariate outliers, and so what we did had to eliminate those for generalizability or assumptions or sort of whatever argument you want to make there, right? But you need to be very clear about what the person was doing, why they were weird, and why you threw them out, right? So let's say, again, I'll go back and think. So let's say you've got someone who is reporting constant heroin, cocaine, and meth use, like basically continuous polysubstance use all day, every day, and then are reporting no functional impairment at work or relationships or anything along those lines, right? Then you say, we had one person that maybe they're just really good at it, but it seems implausible given the data. Might have questions about the reliability of reporting, and so as a consequence, they were eliminated from the set, right? Something along those lines. Other thing, thinking about how we address extreme values, depending on the types of analysis you can get, this can go on and on and on and on, right? If we think about, I've got a variable that has a strong skew, right? So tomorrow you've got a variable with a strong skew, and you say, okay, well, I'm going to drop. We've got 2 cases that are over 4 standard deviations from the mean, so I'm going to get rid of those, right? So you drop those cases, and now you rerun your distribution, right? What just happened now?
It might change your, results.
It could change my results, but if I just drop those 2, if I've got a really strong extreme distribution, the people who I drop because they're 4 standard deviations from the mean, get rid of those. Now all of a sudden, the next people in line, now they're like 3.8 standard deviations from the mean. I'm like, yikes, okay, I'm gonna cut those off. And then I run it again. And now the people who are next in line, now they're 5 standard deviations from the mean, because everything, so it can keep going and going and going and going and going, right? What can end up happening through the screening process is a balance between wanting to identify cases that are going to negatively impact the generalizability of your solution versus having an endless series of cutting and screwing around with stuff and transforming and things along those lines, right? So wanting to be careful and not be aware of what's problematic and what's maybe tolerable, being aware of what the impact on your data are, why things are strange, and then, I don't know, I tend to take a more minimalist approach to data, because anything I do, I'm going to have to, I feel like I need to justify so that no one thinks I'm sort of got my thumb on the scale or something along those lines. So just being mindful as you're taking this approach. All right. Where are we at in terms of time? Linearity is easy. Linearity, you're just assuming that the relation between variables, some combination of variables represented by a straight line, bivariate plots. What you can do, particularly if you're running a model that's got a lot of different variables, you could have a regression model with maybe, this isn't super common in psychology, but you could in sort of econ and some different, like have lots and lots of variables in the model, right? If I've got 30 variables in the model, I don't know if I want to look at all possible bivariate scatter plots between all possible combinations of 30 variables, that would be quite a bit, right? So what I might do is start going through and choosing bivariate plots to take a look at based on evidence and non-normality. Non-normality will start to make your scatter plots look pretty weird. Or theoretical reasons I expect, say, arousal and performance, right, to maybe not have a linear relation with one another. And so I'm going to go through and check these to make sure I haven't violated the linearity assumption. Linearity starts to become important for multivariate normality. Remember that if I'm going to assume that my data is multivariate normal. If each variable in all possible linear combinations, if my individual variables are approximating normality, and all the bivariate relations between all the variables in my model hold a linear relation, and there's linear and homoscedastic, that's when I'm going to start to assume that my data probably reasonably approximate multivariate normality. So this starts to become important, as we'll see. We almost always violate a basic assumption of our regression models. We've taken regression and bastardized it for our own purposes, different than what it was originally developed for, which is fine as long as our data are multivariate normal. So we need to go through and make sure that we're taking a look at scatter plots and things. So if I have nonlinear data, sometimes I might transform, right? If I go through and I transform, that can straighten things out and make sure that the relation between x and y may not follow a linear pattern, but the relation between x and transformed y might be quite linear, right? And then we can go through this as an issue we'll get to in logistic regression, right? The nonlinear transform of those allows us to use a basic GLM with an outcome that's dichotomous, right? So we can use transforms. In some situations, we might dummy code, right? So if I'm interested in the relation between let's take this one right here, okay? If I dummy code, if I look at the relation between, if I dummy x into sort of here and here, right? Now all of a sudden, can I have a nonlinear relation with a dichotomous variable? No, it has to be dichotomous, right? And so I can dummy code and say, I've got a nonlinear relation between x and y, but it looks like at high levels of x, I've got a different relationship than low, and so I just dummy this. So I'm having all these values are now equal to the same group, right? So I get, say, maybe the mean right here, and x values of 0 to 1, I put that in the category of 1, and their mean is up here. So I kind of change things around. It's not great. That paper that you read on dichotomizing continuous variables and why it's bad, we can start to mask certain types of things. So dummy code may not be a great option. Piecewise analyses, this is separating your model into different sections. So here, let's say I'm going to run, I see that I have nonlinearity here. Probably a transform that's super orderly, I'll probably just transform will look better for that, right? But I could also run a piecewise analysis, right? And so Alicia, what I'm saying is here you're saying within your model, from the range of x equals 5 to 0, x has a positive relationship with y. From x 0 to 5, x has a negative relationship with y. And so you're kind of splitting this up. I can take this nonlinear pattern and sort of section it into two different analyses, right?
That's the float light analysis.
What's that?
Float light, I think like they call it.
They call it what?
Float light.
Float line?
Light.
Float light?
Yes.
Okay, cool. I actually haven't done much with it at piecewise analysis. We don't see it a whole lot. Most of our stuff tend to be vaguely correlated with everything in a giant sort of cloud, but there are certain types of things where we can start to go through and say, from this range of my predictor, we have this type of relationship, but then once we hit this, then it starts to change and look a little bit different, so we can do that. Nonlinear analysis, actually if I was looking at this, I might just look at this as if this was like a growth model or something like that. I might just include a quadratic term in there that sort of does a perfect job of accounting for that. problem with nonlinear analyses is that they start to be a little bit more complicated. And so if you're going to do that, you need to be prepared to talk about it in a way that sort of makes sense to other people. Or we can ignore, right? This right here, is that reasonably represented through a straight line? Yeah. Is a straight line perfect? No. But if this is all the data that I have, I don't know if this is the only, this is my set, right? And this is new research. It could be that this is following an actual nonlinear trajectory. I have some actual curvilinear trajectory going on there. That's possible. Or what else could it be?
Heteroscedastic.
Yeah, I have too few people, right? Could just be random stuff in my data. Maybe this specific data set, right? This is like seeing the Virgin Mary in your toast, right? The toast doesn't always have the Virgin Mary, right? It was just that one piece of toast. They kind of looks, you like, CJ's like mine. I think it's like that, right? Like sort of coming up with the obvious sort of analogy here, right? It's just the data, right? The data just kind of did a weird thing, right? I don't know why it did it. It just did, and it's just so what we can start to do, what we want to avoid doing with some of our nonlinear analyses is avoiding overfitting the data, right? We're saying, okay, what I've done is I'm saying that the relation between X and Y always follows this nonlinear pattern, and I've staked my reputation on that. Well, you shouldn't have, because maybe that was just something that happened in that data set, right? And so I've got a really good model that super well fits this data set, but will never fit any other data set nearly as well, because I've capitalized on chance with this. Okay. All right. Let's take a break. We'll finish up with homogeneity and variance stuff. So we're moving through stuff pretty quickly, but a lot of this stuff is covered in the Tobacco chapter. Are people kind of following along and sort of getting the general gist of this? And when we get into regression, we'll get into more sort of types of stuff. Okay. All right. Variance assumption, homogeneity of variance with our grouped data, right? We're assuming that variability in the population is the same across all of our different subpopulations in our groups, right? So based on the data, we're assuming that my condition A has the same variability in my outcome as condition B as condition C, right? And so this is something we've been working with for a while, recognizing it is important, and sort of taking a look there. When we're looking at ungrouped data, we have still have the same assumption. We're just calling it something a little bit different. Talk about it as homoscedasticity, okay? Homoscedasticity with our regression analysis, our ungrouped data, is the assumption that variability in scores for continuous variable y, same across all values of x, okay? So if I'm looking at sort of this graph right here, what I would say is that x and y, the association of x and y is homoscedastic. That means for any individual value of x, the distribution of y is about the same. Okay, it's not perfect. It kind of looks like kind of a cigar kind of shape here. But if I look at this value of x, everybody at this value of x kind of has the same variability. This value of x, same variability. This value of x, same variability. We would talk about this as a homoscedastic relation. Down here in the bottom panel, this is what we would typically see in terms of heteroscedasticity. Okay. Tomorrow, what's going on down here with this pattern relative to what's going on up there?
The variability changes.
Yeah. What's it doing is, as x increases, what's the variability in y doing? It's getting bigger, right? So we see this fan shape, right? So at low values of x, we have pretty minimal variability. But at high values of x, y has a lot of variability, okay? And so what we're doing is when we're assessing this is we're looking at difference in spread and shape in scatter plots. Now this gets more tricky when you're actually using real data for a lot of reasons. But this is just the same, this is no different than your homogeneity and variance assumptions. So let's say I have 0, 1, right? And so this is y, right? And so here, this is my variability, my scores at 0, right? My group 1. Here is variability in my second group, right? And so this is about the same as this. And so would we have a violation of homogeneity and variance there? No, right? So just take this, when we think about homoscedasticity, and just expand this. Now instead of just one group 0 and group 1, let's say this is a continuous variable where people can take any value in between 0 and 1, right? Now all of a sudden, for every single one of these values, 0.5, 0.25, 0.75, right? And anything in between there, variability doesn't matter. So we're talking about the conditional variability of y given x, right? Here, doesn't matter. We can take everybody who has a value of 0.5, and if we look at the variability in y for everybody who has 0.5, it's about the same as everybody who in my sample has a value of 0.25, right? And so homogeneity, variance, and homoscedasticity, they're exact same thing. It's just we talk about it a little bit differently when we're talking about our group versus our ungrouped analyses. Okay. People kind of see the connection there. So if I use violations of univariate normality, it can also often result in heteroscedastic relations, right? So we want to go through and make sure if we have problems with our distributions, we address those before we get to this point. Also, we can see variability in measurement precision, right? What we might see, so for clinical people who take Tara's class, what do we know about the variability of IQ at the far and high end of the scale and the low end of the scale? It's much more variable, right? So if my IQ was deemed to be 130, right? A lot of variability in terms of like, so you say we're looking at IQ and academic performance or something like that, right? What we might see is I'm not claiming to have an IQ. I'm just saying what if. I'd probably be a better teacher, or maybe not. Maybe I'd be a terrible teacher, or worse than I am. But what we might see with this at the low end, let's say 80 to 130, we might see, and this is some sort of functioning, or let's say academic GPA, something like that. What we might find is a lot of variability here, and a lot of variability here, and maybe not so much variability here. Something like that, right? Which would be kind of a weird kind of bench. We don't typically see this type of thing, right? But what we're seeing is sort of problems with my measurement. Some people down here, if I'm sort of low, am I super convinced that my score is this low? 80s maybe not all of it, but at the low end of the scale, the measure gets less reliable, right? Same thing at the high end of the scale, it's less reliable, right? And so if I'm just looking at observed scores, we might get sort of very heteroscedasticity that ends up emerging as a property of my scale. So needing to be careful about that and thinking about the psychometrics of the types of measures that we're using and characteristics, so we can start to understand what's going on if this stuff comes up. Questions about homoscedasticity assumptions? Okay, so violation of homoscedasticity, not fatal. They're going to ruin your day, but it does weaken your analysis, makes things a little bit less robust. My parameter estimates are going to remain unbiased. So my regression coefficients, so the unique effect of x on y, that's not going to be impacted at all. But what we start to see, and this starts to become the issue when we start violating assumptions of our regression models. Where we start to see the impact is in our standard errors, okay? Why are we concerned about potential impact of standard errors? Chrissy?
Because your standard error is directly related to whether or not you're rejecting or failing to reject your null hypothesis.
It's based on my entire inference test is based on sampling distribution of this coefficient, right? And if my standard errors are too small, what's going to happen? You're right.
Yeah.
Because I'm going to reject the null more often than I should, right? I'm going to say I found something different than 0 more often than I should. If my standard error is inflated, what's going to happen?
Type 2.
Type 2, right? I'm going to not identify something as an effect or identify evidence for an effect when maybe I should, or when maybe an effect is there. If my variance decreases with the predictor, right? So as x increases, my variance decreases, so I get kind of a cone shape. This is going to inflate my standard error. If variance increases my predictor, get that traditional fan shape. As x increases, variability in y, or as x increases, variability in y decreases. That can attenuate my standard error, right? So what would I be concerned about the potential impact of this on my standard errors? Okay.
Type 2.
Type 2, yeah. And so what is this? Okay, so here's x is increasing, variability in y is decreasing. So that's going to do what? Attenuate my standard error, right? So what I'm going to do is my standard error is going to be too small. And so what I'm going to do is I'm going to identify effects when I probably shouldn't identify effects, right? So that's going to make the result in my type 1 error.
Okay.
Same something there when it's not. Okay. So looking at heteroscedasticity, bivariate plots, and residuals. We're going to spend a lot of time with the residuals, looking at those. Homogeneity of variance, F-max ratio. We've done this before, right? You guys are doing it right now. Looking at variance across your largest and smallest cell. I've got a balanced design that's being pretty generous in terms of balanced design, 4-to-1, right? F-max of less than 10 is probably okay. With an unbalanced design, F-max of greater than 3 starts to influence your type 1 errors, or excuse me, your type 1 error. Again, if my greatest variance is in the smallest cell, right? So things start to go through and impact stuff there. Okay. So solutions for my if I find violations of homogeneity of variance, or excuse me, or homoscedasticity, I can transform my data if it's largely a function of nonlinear or non-normality in my variables. I can use analyses that correct for the violation of homogeneity of variance, right? So in our ANOVA models, what did we do, Alicia, when we found violations of homogeneity of variance for our t-tests? Think about that output. What were we able to do? So there should be hopefully t-tests going on currently in this set. What do we do if we see violation of homogeneity of variance? What do we do?
You look at the row that says the variance not assumed.
Yeah, equal variance not assumed, right? So we go down to that second row that has, we're seeing an adjustment on my degrees of freedom in my test statistic that recognizes that I violated the homogeneity variance assumption, right? With our ANOVA models, we have Welch's test. Remember, for the Levine's test violation of homogeneity variance, we request a Welch test, which is robust to that. In regression, we can use robust standard errors, right? This is one of the things that SATA does fairly easily that will address if I have homogeneity violations of, or if I have heteroscedastic residuals. That's a pretty easy thing to do. I think you can jimmy it out of SPSS. I haven't been able to figure out how to do it just yet. So some things take that into effect a little bit better. Or other thing too is you need a different estimator, right? We talked about generalized least squares as being an approach that people will use when they have heteroscedasticity in their residuals. Generalized least squares does a little bit better dealing with that. Under circumstances, you kind of need a big sample for it. So different ways to address it, but the thing is it's important to recognize it and not pretend that it's not there, and maybe try and understand what's actually going on so we can sort of develop an approach to dealing with it. More stringent alpha. I guess if you see a fan-like pattern that suggests that I might have attenuated standard errors, you can say, well, I'm going to set my alpha level to 0.01 then in terms of identifying evidence for or against or things along those lines. All right. I think this is it. Last thing we're going to talk about, multicollinearity, singularity. Okay. Multicollinearity, high correlations between variables. Singularity, variables are redundant. Correlation is 1, right? There's a direct linear dependency in either 2 or a combination of variables. So 2 variables, I basically have entered the same variable twice into a model. That's pretty easy to identify, right? When it's a combination of variables, right? So let's go back to, so say CJ is looking at esteem, right? He's interested in these 4 subscales of esteem, but then he drops into the total score, which is just the sum of the 3 other scores, right? Individually, any one of those scores may be actually completely uncorrelated with one another. When I've got all 3 of them in there, those 3 up add to the 4, and now all of a sudden I'm going to have a singularity or something close to it because of what's going on. So that can be a little bit tricky to identify. We're not going to get into matrix algebra, but basically what ends up happening, and the problem is that within the guts of regression, so the mathematical underpinnings, we've got redundant variables. And what ends up happening within our matrix algebra is that we have less information than our model is suggesting that we have, okay? And we would say that the matrix is not full rank. We have less data in the matrix than we think that we have, and so what ends up happening within the context of matrix algebra, this ends up sort of functionally being basically trying to avoid things by 0. Things start to get really wild and unstable when we start to do this, and so we start to have problems with our standard errors. So in this matrix, let's say this is person 1, so we've got participant 1, participant 2 on variable x and x1 and x2, right? What's going on with this? Do we actually have 2 variables in here? No, why not, Sean?
The second one just multiplied by 4. The first
What's
one,
that?
The second variable is just the first one multiplied by 4.
Yeah, right. This variable, x1, is redundant with x2. x2 is just x1 multiplied by 4, right? And so even though we've told the model that we have 2 variables in it, we actually don't. We have one that's, we have a variable that's a linear transform to the other variable, and so what's going to happen is that I'm going to get some sort of error term, right? So we've got a singularity going on in this, right? And so this is basically what's going on in our regression models where we start to add variables that are highly, highly correlated with one another. Okay? So we can identify collinearity through bivariate correlations, right? So if I go through, before I run my regression model, I'm going to look at between my predictors. I'm going to look and see sort of what the correlations are between them. And if I have one variable that's the redundant or sort of the linear of the other one, so say I have 2 sex variables in there, one where women are 0, men are 1, and another one where men are 1 and women are 0, and I accidentally just drop both of them in because I made a mistake, I'll get a correlation of 1 between those 2 variables. I'm like, oh, whoops, that's a problem, right? But maybe I have 2 measures that are called different things but are actually measuring the same thing, and I'm like, oh, whoops, this depression measure is actually just a negative affect measure functionally. Maybe I shouldn't have both of those in my model, right? So looking at your bivariate correlations there. Okay. Now, if I've got multiple variables, however, this can start to be a little bit harder to detect, right? So the combination of x1, 2, and 3 is collinear with, or highly, highly correlated with x4. That's when we start to need to be using some of our regression techniques to ferret some of this stuff out. Basically, what's going on is in the gut sequence model, these diagnostics will take, let's say I've got 4 predictors in my model. I've got x1, x2, x3, and x4. What we're going to do is we're going to take x4 and regress it onto x1, 2, and 3 and see what our r-squared is. What would happen, what would our r-squared be if we had a problem? Yeah, it'd be something really big, right? Maybe not 1, but maybe something like 0.95 or something like that, saying that variables x1, x2, x3 share 95% of the total variability in x4. That's problematic, right? And then the model is going to take x3, regress it onto x1, 2, and 4, x2, regress it onto x1, x3, and x4. So we're going through and taking a look at that squared multiple correlation. And that high squared multiple correlation is going to suggest considerable overlap there. Now, what we'll get from SPSS and from different programs is we'll get a couple of different statistics. First one is going to be called tolerance. Tolerance is just 1 minus the squared multiple correlation of that predictor regressed on all the other predictors in the model. Okay? If I have tolerance values that are less than or equal to 0.1, that starts to suggest, that does suggest problematic collinearity. So again, if I have x1, x2, x3, x4, okay? And I take x4 equals x1 plus x2 plus x3, okay? Right, regress this one onto my other predictors, and this model gives me an r squared for x4 equal to 0.95, okay? And this is my, r squared is my squared multiple correlation, okay? What's my tolerance going to be here for x4? 0.5. Yeah, 0.05, right? And so that would suggest lots of problems with this, okay? And so this is just wanting you to understand where these tolerance values are coming from, what they mean, things along these lines, okay? So I've got a little asterisk here. It's basically what they're saying, like tolerance values less than 0.1 indicate of problematic collinearity. If you get anything that's even like remotely close within shouting distance of this, this should be triggering red flags to say, hey, I've got redundant variables in there, right? And this is a big thing with psychological science. We love to come up with constructs and call them different things, and they're actually not different things, they're the same thing, right? And just because I call it a scale something, doesn't mean that's actually what it's measuring, right? And because everything in psychological science is related to everything else, want to be very careful that we don't have conceptually redundant measurements in our models, because it starts to have negative impact with that stuff. Other thing other statistic that we'll get is variance inflation factor. This is just 1 divided by your tolerance, right? So it's not really all that different. It just gives a different kind of look at stuff. If I take the square root of my variance inflation factor, this is going to provide an index of the extent to which my variance of my coefficient is inflated as a result of collinearity, right? And what am I talking about in the variance of my coefficient? What is the variance of my coefficient? My coefficient is just one number, but if I ran this model over and over and over and over and over again, what would I get? Sampling distribution coefficients, right? So the variance of my coefficient is what? What else do we call this?
Standard deviation. Standard error.
Standard error. There we go. Close. You gave me like the head shake, and I like fell for it, and made me look like a jerk in front of all of YouTube, in front of all 7 people who watch this. I look like a jerk. But yeah. So basically, what is going on here? If I take the square root of my VIF, it's going to give me an extent to which measure of sort of the potential inflation of my standard error. So if I got a VIF of 9, suggests that the standard error, my coefficient, my target predictor, about 3 times the size of it would be if I had VIF of 1. Now VIF of 1 is going to be my predictor is uncorrelated with anything else in the model, right? And so this starts to indicate the problem with collinearity. We start to get very, very large and unstable standard errors when our predictors are too highly correlated. Again, a VIF greater than 10 indicative of problematic collinearity. Again, anything that even starts to get anywhere that would be close to anything like that is something that you should start considering carefully about what did I put in my model, does this make sense, and trying to figure out why my variables are what variables are lined up with one another on this. So again, most of the time, if I put something in that's just not going to work, you'll hit a point where your regression model or your program will refuse to spit something out, but that's usually tolerance values anywhere from 0.01 to 0.001. Like, just because your model gives you an output doesn't mean that that's a good thing. You should be looking at some of these other things, and again, thinking conceptually, what have I put in my model? Why do I really need 5 measures of the same construct in my model? What's going on with that? Questions about the technical linearity stuff? Solutions. If my goal is prediction, if the only thing that I want to do, this is a straight data-driven model, and all I'm interested in is predicting some outcome, I can ignore it. Because collinearity, your coefficients are fine. There's no, your coefficients themselves aren't biased. The problem is the bias in my standard error, okay? But if I'm not interested in testing the unique effect of individual predictors, who cares? I can just ignore it, right? Yeah.
Might collinearity attribute the effect to one or the other of the variables?
Yeah, it jumps it all over the place, yeah. And so that starts to become problematic. But if the goal of my regression equation is to predict some outcome, don't care, right? Because it will do that unbiasedly, but all my standard errors will be out of whack. Yeah. So what I can do is I can check data for errors to make sure that I coded things right, make sure that I don't have scales in there that are redundant with other scales. If I have redundant variables, so I've got 2 different constructs that I thought were theoretically important, but it turns out that the measurement, either those constructs or the measurement of those constructs is redundant with one another. I need to make a hard choice on which one of those ones I really need in there. What I can do, if I have say 3 variables that are all collinear with one another, I could sum those up or average those. I don't like this because if tomorrow's like, oh, I have 3 measures of ADHD in my model, and so and they were collinear, so I added them all up and just took a composite of the 3. I'd probably ask you why you need 3 of those in there in the first place, right? If you've got 3 measures of their collinearity to the point that they're causing problems, you need to be thinking about what did I do and why they all need to be in there. But you'll see this happen sometimes. Well, we found and this is a more data-driven approach, we found that these 3 predictors were collinear with one another, and so what we did is we just took the composite of those 3 and left it in the model. I don't know. I'm having a hard time thinking about why you would do that as opposed to just picking one and leaving it there, but whatever. Other thing, using principal component analysis to create component scores. It's another thing, right? If I had a model with a lot of predictors, right, I could potentially use a PCA to go through and say, okay, what I've got is I've got component scores, so basically not factor scores, but for your purposes right now, think about factor scores that are combinations of sort of these 3, and then I'm going to go through and use that in my regression model. Again, these are more data-driven approaches that are antithetical to the types of things that we're doing in psychological science. Is usually what we're interested in testing theory, right? Like this theory predicts that this thing, or suggests that this should be related to this thing. Is it? Do we have evidence for this, right? And so if I just smash together 4 different measures, now it starts to become questionable what I'm actually measuring. and what that means even if I do find a relation. All right, so these all up to this point are screening stuff that went through, Tabashir Fidel went through this stuff. This is stuff that we are often doing with our observed data, right? With our observed scores. Now we're gonna do, when we get into our regression model, we're gonna have some concerns with our observed scores, right? But we're also gonna be spending a lot of time with our residuals we will represent.
So compare the difference from your values in relation to your regression line.
Right. It's the deviation between my observed value of y and my predicted value of y, right? And when we get into my assumptions of regression, that error term, right? The difference, how far we were off on the prediction of each and every person in my sample starts to become important, because my assumptions about my regression almost always are dealing with some aspect of the residuals, okay? And so when we get into this, it starts to become important. Thing about everything we've talked up to this point is sort of basic screening, sort of looking at our observed variables and our observed data. When we transition now into our regression assumptions, what we're doing is we're looking at sort of the distribution of those residuals, those error terms, and making sure that those are acting appropriately in order to be able to make strong conclusions based on our models. Okay. So, basic assumptions of regression. Predictor variables, fixed non-random variables measured without error with variance greater than 0. There's a lot of stuff going on in there, okay? So let's unpack this for a minute. Predictor variables, so my predictors are fixed non-random variables. What does that mean?
They don't have a distribution.
What's that?
They don't have a distribution, we know what they are.
Well, they have a distribution, but they're going to be, well, yeah, but you got any distribution they want, right?
Mm.
But are these values of X things that just happen to come up? No, these are things I systematically selected for, right? So the basic assumption of regression is that we're using fixed non-random predictors measured without error. What does that mean?
Wrong.
What's that?
You said wrong.
What's wrong?
It's definitely measured with some error.
Okay, so yeah, so the measurement of that, it said my assessment is perfect, right? I have perfect assessment of my predictor variables with variance greater than 0. What does that mean?
You're assuming some variability.
Yeah, right? Because if all values of x1 are 5, then that's not a predictor, that's a constant. That's not a variable, it's a constant, I can't use it, right? So already, right off the bat, we're identifying that maybe we have systematic problems with our assumptions based on how we perform regression models. Okay? Second assumption is that our errors, our residuals, are going to be normally distributed. Okay? So that residual, the deviation of my predicted value from my observed value, I'm assuming a normal distribution there. Okay? The variance of my errors is going to be constant for all values of x. Okay? So my error term, for all values of x, errors are going to be constant. So it doesn't matter what level my predictor is. I'm assuming that across all values of my predictor, the variability of my error is going to be identical across. And this is getting to my homoscedasticity of my errors. Okay? If I have heteroscedastic errors, it means as x increases, I get farther, my predictions get worse and worse and worse and worse as things increase. Okay? And so we can think about this as equal conditional variances for a fixed x, right? Tomorrow I'm going to pick on you, right? You've done a wonderful job of talking about conditional effects and things like that. Conditional variances on x, that means conditional on x, the variability of y is identical conditional on x. So for every single x variable, the variability of y is going to be the same, right? Or the variability of my errors is going to be the same. I'm assuming that my errors are independent, okay? So however far I'm off in my prediction of Chris's value has nothing to do with the error of my prediction of Sile's value with Chris's value, with Tamara's, everybody's errors, so that the errors are uncorrelated with one another. There's not systematic links between the errors across independent individuals in my sample. Right? We should talk about this as autocorrelation. And then I've got two final ones here. These ones are in red because we can't actually test these. These are going to be true by definition, but not true in reality. We're assuming that my errors are going to be uncorrelated with my observed value of x, right? So that how far I'm off is not systematically related to the level of my predictor. And I'm also expecting that my expected value of my error in the population is equal to 0. Right? This means that on average, my value of error, I'm going to miss above sometimes, I'm going to miss below sometimes, but overall I'm assuming that the population value, if I were to run this model in the entire population, my error would turn out to, reduce to 0 with this. So these are my primary regression assumptions. We're going to work through each one of these individually, but any questions about this? Okay. So, basic assumptions here. If I've met assumptions 1, 3 through 6, so I've fixed non-random variables, homoscedastic errors, independent error of each other, independent error of observed x, and 0 population error, then I would say that my regression coefficients are blue. They're the best linear unbiased estimates. Okay, you hear this at some point if you get into methods literature, right? It just means that these estimates are best I can do, and they're unbiased, so they're pretty good. I like this, right? When my regression is blue, I'm pretty pumped about it, right? Residuals meeting assumptions 3 and 4 are going to be identified, so then I would say that my errors are independently and identically distributed. Okay, it's important for our standard errors. And normality of my errors is important for making sure that I have unbiased standard errors. Okay, my standard errors are going to be important for significance testing, right? Anytime, and this is sort of the primary concern is with my standard errors, because I'm assuming that I'm running this regression model to try and sort of make claims of evidence for some relation between my predictor and my outcome that's some non-zero value, and if my normality of my errors are thrown off, then I start to question whether or not my inference tests are accurate. Okay? So my concerns when I'm working through this stuff, the whole reason we're doing this, 2 questions. Estimates of population regression coefficients unbiased, that regression coefficient. Have I is there systematic bias in the estimate of the unique relation between x and y, right? I'm concerned about that if I violate it. And then our estimates of the standard error for the regression coefficients and the mean squared residuals unbiased, okay? So this is my estimate of should the actual association correct. This is my tests of those associations are going to be correct. Those are the 2 things that we're primarily concerned with. Questions? All right. Sean doesn't think it's funny. It's funny, Sean.
I don't get it.
Here. Blue, I want my regression to be blue. You can hurt you in other ways. It's actually creepy. Whatever. All right. Violations. Fixed effects. Okay. My assumption is that my predictor variables are fixed non-random variables measured without error with variance greater than 0. Okay. My fixed effects model is in sort of the original development of regression as a technique was centered around this idea of running a fixed effects model. And what we're assuming is that my predictors have specified values sampled systematically with all possible / relevant values of x captured in all subsequent replications. Okay. What this is saying is that regression as an analytic strategy is assuming that whatever my Sally, give me a predictor.
Okay. Happiness.
Happiness, okay. So whatever measure, I'm measuring happiness. Whatever my happiness scale is, regression is assuming that I've included systematically all relevant values of happiness, either possible or relevant for this project. Every single value of happiness that there is represented in my study, and I've systematically selected people for certain levels of happiness to include in my study, okay? I'm also assuming that I've measured happiness without error, right? And so in my fixed effects regression model, if I've systematically sampled all possible relevant values of my predictor, am I gonna have sort of any type of expected distribution of my predictor? No. Regression at its core has no assumptions about the predictors of X, right? It could be, let's say I've gone through and what I've done is I've sampled, systematically selected cases with 20 cases with all possible values of happiness, right? And so then what's my distribution of happiness look like? It's flat, right? If I've got 10 cases for all possible values, so I've got, say it's an orbital scale, so 1 through 10, right? And so I've got 10 of 1, 10 of 2, 10 of 3, 10 of 4, 10 of 5. And so the distribution of happiness in my fixed regression model is 5. It's a square distribution, right? So there's not any type of systematic thing going on. And so basically what I've got is I've got color, right? And so I've gone through and systematically included 20 gumballs of each color, and that's my sample right there, right? So I've got, how many colors are there? I don't know, 5, let's say 5. I've got 5 colors of gumballs. What I've done is I've systematically grabbed 5 gumballs, or excuse me, 20 gumballs of each of the 5 colors, and that's my sample. Is that how we run our regression models? Is that what we do when we sample people? No, what do we do when we sample people?
Whoever wants to.
Yeah, right? We just kind of say, hey, come on in, right? And like, what value of X do you have? I don't even want to know. I'm just going to have you come in and I'm just going to collect it. We're just going to see what happens, right? And so what type of variable is this?
Predictor.
It is a predictor. So we've got a fixed model, or a fixed variable. What's this?
Random.
Yeah. Did you whisper random back there? Okay. You can't. You gotta yell. I'm way over here. Or you stand right next to you. I just can lecture from like.
That's okay.
Okay. So yell. What level threats now against people? Right. So what we typically do is we have random variables, right? We're selecting people. We're just having people come in. I don't know before my data is collected what variables or what values of my variable are going to be represented in my model, right? And so because we almost always violate this fixed effects assumption, but what ends up happening is my model and my estimates are still unbiased as long as the variables in my model are multivariate normal, okay? So this fixed effects assumption, we always violate it, almost always, because that's not how we conduct analyses, right? But what we've done is we've hijacked regression and we've included random variables as predictors instead of fixed effects predictors. But it's fine as long as our data, our predictors, the set of predictors will end up being multivariate normal. Okay. So this first part, we violate that, but we're cool as long as we're multivariate normal. Okay. Second piece, we're assuming that our predictors are measured without error. So we're going through like basic measurement theory. We can say that any observed value of X that I have, okay, CJ's got a measure of hopelessness or something like that, right? So your measure of hopelessness. You've got Alicia's hopelessness score. Appropriate. We're in the depths of regression diagnosis, right? That hopelessness score, right, is going to be a function of Alicia's true hopelessness, right? Like the sort of unknowable value plus some sort of error there, okay? And this is our measurement error, right? Same thing with IQ. I measure IQ. IQ is going to be, my IQ score is going to be some function of my true ability plus or minus error that's associated with the test, okay? And so if I have measurement error in my outcome, it doesn't bias the parameters, but it does lead to inflated standard errors, right? If I'm measuring my outcome with error, what I've got is more variability that's added due to just measurement stuff that's sort of added in. And so if my outcome variable is not measured well, if I'm not using a strong psychometric measure, I can expect that to increase and inflate my standard errors. And if my standard errors are increased, what's that going to do to my overall model? It's going to make it harder to identify effects, right? Because I'm going to have more variability in that. So it doesn't bias the parameter, but it does inflate standard errors. But if I do have measurement error in X, it does result in biased parameter estimates, right? If my parameter estimate, my regression coefficient, say be y given X, okay? So this is just the regression of my y onto my X variable. So this is just my coefficient, my regression coefficient. My regression coefficient that I observe is going to be some value, some function of the population value. So what the true population coefficient is for that, plus the reliability of my measure, or sort of multiplied by the reliability of my measure, okay? And so as a consequence, if this value, what's the max reliability, if I have perfect reliability, what's my reliability estimate? 1, right? So as soon as that's not, as soon as that value is not 1, what happens to the estimation of my population effect? It decreases, right? If I multiply any number by a value that's less than 1, it attenuates it, right? And so what ends up happening, as I start to have measurement error in my predictors, it's going to systematically attenuate on the whole. So the sampling distribution, it's going to make my regression coefficients smaller than I would expect. It's going to attenuate them. And if my measurement error is, if the reliability of my measurements is real bad, let's say this is 0.5, basically I'm cutting my population estimate in half, right? And so this is why we're assuming, the model itself is assuming that my predictors are measured without error, right? Because if I start having error in my predictor values, it attenuates my estimates, right? And it makes it look like I have weaker associations than I probably would in the absence of measurement error, okay? So measurement error is going to increase my residual variance, attenuates my R squared. Individual coefficients, it's kind of complicated, depending on how sort of error starts to come through. But what we know is sort of the problem with error in my measurement characteristic. This starts to have a direct impact on the estimation of my regression coefficients. Okay, so this is why it's important when we're thinking about statistics and procedures and things like that. We can't divorce it from methods. This is why when we're going through choosing our studies, we want to do the very best that we can to create good measures to reduce potential bias in our estimators, bias in our tests, and things along those lines. Questions about fixed effects and stuff? Yeah.
If our sample is taken randomly, doesn't that cover this violation?
Where are you finding random samples?
Like if you assign the population numbers and you pull numbers from a hat and you say, okay, I'm going to use this one.
Are you doing those types of analyses?
It probably doesn't apply. Maybe it doesn't. Maybe it doesn't apply.
I mean, in theory, yeah, right. But in actual practice, we never do, right? Even the census is not sort of even census stuff is not a truly random
quality
sample.
control.
What's that?
Quality control. You
Quality
can do
control.
that, right?
This starts to get better, yeah. And so this is something that from a theoretical standpoint is something that exists and something that's unavoidable, right? So what we're wanting to do is think about sort of just doing the best that we can to try and minimize things, right? Like, and this is what happens in applied statistics. It's never good, right? It's never going to be perfect. All we can do is do our best in terms of methods to try and minimize this, and so this starts to become a straight up methods issue, right? So once the data is collected, I can't, there are formulas for disattenuation of error that are sort of okay sometimes and things like that, but so the best remedy is just making sure that you're doing your best to try and collect measures that are good. I don't know if you get this in marketing research, but sometimes for, I don't know, experimental does a little bit better job of controlling stuff. Sometimes in clinical stuff, someone will be like, oh, I wanted to measure sort of this construct, so I just came up with a 5-item scale that is face valid that should get this thing, right? And so if I do that, I can do that, I guess, right? But probably the better thing would have been to do is just to get a validated scale that has some sort of known properties, right? And it's getting harder to get away with that type of stuff, but it's something we usually come up in research from time to time.
I may have done something similar to that.
May have contributed to that.
Right. So Chris is
Tried to adapt a well-known scale and then tried to adapt it for something else. So I think it's a little better.
what do you have plans for spring break?
Not really.
Yeah, good, because you need stat prison for that. Hollywood stat prison.
I think
A week in stat prison for just making up a scale.
I'll send it to you. It's pretty similar to the other scale. It's just adapted.
Right, okay, like, you know what, I got a ton of products I'll sell you. Like, they're pretty similar to what, don't worry about it, it's fine, it'll probably work.
Sounds great. I would love it. That sounds like you did some research and it worked out really well for you.
It's validated for another population, but it's validated.
Well, and this is the thing too, and that starts to get into methodological psychometric stuff that does start to become a question with this stuff, and so I think we clearly.
So, for example, I'm just curious, for example, if you're looking at like caregivers in general, but you wanted to use it for like caregivers of dementia patients.
Yeah.
Would you be able, you would still be able to?
I don't know. That sounds like a literature situation that you would need to go through and do. Best case scenario that's been valid, the measure's been validated in the population that you're going to go through and use, right? But again, think about like for my area, right? One of the things people love to do is give PCLs to people who may or may not have actually experienced some sort of criterionic trauma, right? You can do it. People say PCL has great psychometric properties. Yeah, when you give it appropriately to the people who need to have it, right? Same type of thing you, at least clinical folks, you've all just last semester been through assessment, right? People say, oh, the waste has amazing properties. Well, the waste has amazing properties if you know how to give it, you've administered it correctly to people who it was intended to be given to, right? If I don't, if I just grab some geek off the street and just say, hey, here's the test kit, go nuts, right? All of a sudden, like, so the psychometrics are not a property of the measure, they're a property of the administration procedure, right? And so needing to think carefully about those things. So, Chris, I'm sorry that Chris called you out and made fun of you.
I think I did a great job.
Very nonverbal.
Yeah, I think if you saw it, you would give me a round of applause. This is not the first or last time I will receive a round of applause.
All right. A lot of other things. Okay. Talking about normal error distributions. Okay. We're assuming that my errors, my residuals are going to be normally distributed across all values of x. This is an underlying assumption of your significance of your R squared, your model R squared, your individual coefficients. We can get non-normal errors in our data from a lot of different things. We can have sampling strategy, right? I might have only assessed, say I'm looking at depression, I only assess people with very severe depression, right? So let's say this is some sort of functional outcome, and this is super depressed and crazy depressed. Right? I just grab the top end of the scale, right? And I might find that, you know, my regression line looks something like that. It's probably going to be attenuated, not as strong as it's going to be because I've got restricted range, right? But if my, this is the low level of my functioning, if my regression model misses, where's it's going to miss? It's right down there at the bottom. It's gonna miss up here, right? I'm gonna have people with, when I do have errors, so right here is maybe where most of my values are, right? But if I miss, they're gonna be more likely to miss above than miss below, right? And so what ends up happening, I can have a distribution of errors where everything's kind of clustered around here, but when I miss, they tend to go up, right? And so what we can do, so we can have super severe here, or the same thing, heroin usage children, I don't know, it's almost everybody's gonna be 0, right? So let's say I'm looking at heroin use in like middle schoolers, right? In general, almost everybody's gonna be no, right? But can I have less than no? No. Some people are gonna have it, and sort of when I miss, it's gonna be too high, right? So when my errors are gonna be missing, they're all gonna be in the wrong direction, right? So, oh, here, this is a better thing than what I just drew on the board. But again, so let's say here's depression, here's life satisfaction. And let's say I just captured just people who are very, 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 very depressed. Like, let's say I'm doing this, people where they're coming like right into the front end of inpatient treatment, right? Here is my depression scale from 0 up, super, super depressed to 5, sort of extremely depressed. And here's life satisfaction. Here's my regression line, right? Here's where everybody is. But when I miss, where are my residuals more likely to, or where are my residuals pulling out? They're all up here, right? So what I've got is non-normal residuals, right? So what I've got here is some floor effect, where when I'm wrong, my observed values are systematically exceeding sort of my expected values within the context of this. Well, yeah, same thing. Age and heroin use, let's say this is 10 to 18 or something like that. Yeah, mostly no, but when I miss, it's all up above, right? And so what ends up happening is it's going to contribute to residuals that where my errors are not normal. My errors are skewed positively here, right? And so regression coefficients are unaffected, but I'm going to result in depression of corresponding standard errors. Okay? And again, if I've got depression in my standard errors, what's that going to do to my statistical tests? Make them too big, right? I'm going to have type 1 errors where I'm over-identifying things where I probably shouldn't. Also, if I have small samples, non-normality in my residuals can go ahead and depress my R-squared value there as well. Okay. So we're concerned about this. You know, people see kind of what we're looking at in terms of residuals and sort of normality in my residuals. Okay. Constant error variance, okay? What I'm saying is my variance of my residuals is consistent for all my values of X. This is similar to the homoscedasticity principle that we had talked about before. Difference here is that we're talking about homoscedasticity of our residuals as opposed to observed scores. Again, what we're hoping is that if I have a plot of my expected values versus my residuals, that I don't want to see systematic spread, right? Where at high ends of my predicted values, I've got lots of variability in my residuals versus at the low end of my predicted values, they're lower here. Okay? So again, I can have measurement error, IQ and achievement might start to create weird fans, or if I've omitted something, right? This gets into proper specification of my model. Let's say I have gone through I'm looking at income and age. I see this and that's the pattern that I'm getting, right? What's an important variable in the relation between age and income that I've missed out on? Let's say this is 20 to 65. Why am I seeing so much more variability as I increase relative to the low end. What's that?
If some people are retired.
Some people are retired, okay. Yeah, they would probably get towards the end there within, but if we're saying 65 is retirement age, what's going on? What variable am I not accounting for that I need to in this model?
Employment status?
What's that?
Employment status?
Employment status, what might be a proxy for employment status? Or not a proxy, or, so we'll say income employment is a proxy for income.
Years work.
Years worked, that's gonna be kind of get with age.
Education.
What's that?
Education, maybe?
Education, there we go, right? Because as people start to go through, if I say have my GED, right? By the time I get to 65, a lot of the variability that we're gonna see here is gonna be based on people's education level, right? People who we would assume to have higher levels of education are gonna probably have higher levels. People who have sort of relatively low education are gonna have low. Down here at 20, we see much variability in what, like, I don't know, 20% sort of in college or out of college, and maybe sort of if I'm 18, I'm going through working gas and oil, I'm making actually quite a bit more than anybody who's in college at any point in time, right? So what we can do is if we have a model that's missing a key variable that should be in there, but it's not, what we can see is that our model, as our predictor increases, we get a lot of variability in our residuals. We get farther and farther. When we miss, we're farther and farther off. But it's because we've omitted something important out of that model. And so again, another reason for when we're going through and looking about at our residuals and our models and doing this stuff, thinking about, have we missed something? Is there something that we didn't take into account as we're working through stuff? So if I have non-constant error variance, right? I have heteroscedasticity in my residuals. Again, regression coefficients are unbiased. So my regression coefficients are fine, but my standard errors bias in the direction of the relation of the errors to the predictor. So if my error variance increases as my predictor increases, it depresses my standard errors. So here, I would have concern that my test of the effective age on, or the relation of age on income would be, my test statistic would be too big, because I would expect my standard errors to be depressed. If I flip it around, if I start big and band down, kind of funnel down like that, then I would worry about my standard errors being too big. All right. Questions about homoscedasticity of errors? All right. Errors are assumed to be independent of one another. Okay. Think about this as autocorrelation. Well, a couple different types of dependency. What we don't want is my error for this observation to be different than related error of this observation to be related to error of this observation. Think about this as autocorrelation. If I've got measurements of the same person over time, right? What we have here is temporal autocorrelation. So I've got Alicia at time 1, Alicia at time 2, and Alicia at time 3. My model predicting Alicia's scores, my error in predicting Alicia at time 1 is probably going to be associated with my error in predicting Alicia at time 2, probably associated with my error in predicting Alicia at time 3. And so what we've got within individuals, we see temporal autocorrelation where my errors are sort of systematically related to future errors in some sort of way. Right? And what we see is observations observed more closely in time, more strongly correlated than observations farther apart. We talked about this with the repeated measures in terms of sphericity and along these lines. Right? We can also see observations among correlation of errors in observations made of different people sharing a similar environment. So this is spatial autocorrelation, right? So if I'm tomorrow and I'm doing like kid-based research in terms of schools, right? And I'm going through and I've gone through, and in my sample I have 10 third grade classrooms, right? And I'm looking at behavioral outcomes in each one of those, right? What I might find is that I have some correlation in my errors between kids that are observed within a common classroom. Why is that? What's that?
Like how their teacher is?
How their teacher is, what the setting is, how they relate to one another, right? And so so the relation, sort of the association between errors between two individuals within a given classroom are probably going to be more tightly correlated than any average correlation from this individual in this classroom and that individual in that classroom, right? And so what we see when we have autocorrelation, again, regression coefficients unaffected for the most part. Regression coefficients are fine, but my standard errors start to become impacted. The problem when we have temporal autocorrelation, spatial autocorrelation, we can have substantial underestimation of my standard errors. And then what happens? Then I've got two little tests for everything. I'm finding all sorts of things and identifying evidence for all sorts of things when I probably shouldn't be. This is an issue that we're definitely generally deal with this as part of a methods issue, right? So if I'm running an analysis that involves a repeated assessment, I recognize I have a repeated assessment, and I'm going to use a technique that addresses the temporal autocorrelation of Alicia's errors from time 1 to time 2 to time 3. Or if I'm doing structural analyses or organizational research where I'm looking at individuals nested in units, nested in sort of something else, I recognize that, and I'm using things like hierarchical or some multi-level models and things that account for some of that error structure there. But it would be inappropriate for Tamara to just take her research where she's got individuals nested in classrooms and just run this in a straight regression model, because that's going to be a violation of her errors assumptions there. Independent errors, errors uncorrelated with observed values of X. Observations and errors, this is something we can test directly with our model, but this is going to be a direct product of the correct specification of your regression. Okay? We say that our model is correctly specified if I've included all the predictors that need to be included, I've excluded all the stuff that doesn't need to be included, and I've correctly specified the form of my relation. If I've done this, then so I can assume that my errors are uncorrelated with my observed values of X. Okay? But this is untestable. This comes from a theoretical basis, right? So again, CJ, you're interested in like your research is interest, motivation, stuff. What is it?
Yeah, self-regulation.
Self-regulation. Okay. So if you have some measure of self-regulation, right? It's incumbent on you to know what types of factors are important in determining self-regulation. Like what does research suggest, what does theories suggest, and if I'm putting together a model, if there's something relevant, I need to have it in that model and be accounting for it. Because if I don't, if I've omitted something, what I could have is a situation where my errors or my residuals are systematically associated with some value of X because I've omitted something from that model. Okay? Do we do this? No, we don't do this. We're like, oh, I have this, and it's not just, so is it totally to figure out a poster idea, here's some data, figure it out, right? She's limited to the variables that are in that set, right? So she might be interested in some outcome, and so if you went through and took a look back, well, for this outcome, I should have this, and this in the model. We don't. Do you not run the study? No, you still run the study. But we have a problem that we have a specification error going on with this. Okay. Consequences of misspecification are complex, can lead to all sorts of different bias. Okay. In other areas, talking with Sasha and econ, right, to omitted variable bias is a big thing, right? For different reasons than to what they are with us. But if I'm wanting to sort of make some sort of causal argument, I sure better make sure that I've got all the necessary variables in there. Last one, zero population error. Expected value of population error in the population is 0. OLS guarantees that my average, the average of my residuals is 0. Okay, this doesn't mean that the population variance, the population error is going to be 0, right? Again, this isn't something that we can test, but we can start to see examples where this might be the case. Let's say I'm interested. Okay, we'll go back to you, Chris. You're measuring weight, right? But your weight, scale is 5 pounds heavy. Okay, and so for everybody you assess, they're going to be 5 pounds off. Now your OLS is going to give you a 0 residual, but in actual fact, your estimation of population intercept, right, so the mean value for the case is going to be 5 pounds off, right? This isn't something we generally worry about, but it's something that can come up. Or let's go back and talk about, so we kid ADHD type of stuff. Let's say I'm interested in playground regression, right? And what I find is that my coding of regression acts starts to be more reliable for kids with low levels of regression than kids with high levels of regression. You've done STP stuff before, right?
I'm going to.
You're going to, okay. Yeah, when you got a bunch of kids running around, you're trying to flag code aggressive behavior, when it's all over the place, you're gonna miss something. It's just, we're gonna have systematic biases because for the people who are highly exhibiting high levels of regression, we're gonna be less accurate at coding those than the kids who never regress on anybody else. So violations in this, we can have estimates and parameters and standard errors, typically not severe for most cases. It sort of most often impacts the intercept. We're not usually concerned too much about the intercept and things, but not something we spend a lot of time on in psychological science, but something that is out there. In terms of verifying our assumptions, violations of fixed effect is ignorable when our data are multivariate normal, right? So we want to go through in our screening, we want to make sure that each variable, all linear combinations of variables, normally distributed in homoscedastic, okay? And we can go through and take a look at this and assess this. And we want to make sure our residuals are normally distributed and independent of one another, okay? And so there are techniques we can go through and take a look at this. Linearity assumptions, looking at normal and homoscedastic errors. We'll look at these through some residual plots that we'll talk about. Generally what we'll do, this is fine to do if we've got one predictor and one outcome, but that's rarely the model that we look at. And so what we're going to do is we're going to look at the plot of our standardized predictive scores by our standardized residuals. We're going to look at some normal probability plots, histograms. What we want us to do is make sure that things are sort of relatively normal in terms of their distribution, and that those residual plots are showing constant variance across all of our predicted values. Concerns with our independent errors. This is based on designs, as I had mentioned, with known or likely violations, repeat measure stuff. We've got temporal autocorrelation. We need to use a specific tool for that. If I have hierarchical data, HLM multi-level models, right, for looking at individuals nested in this group and nested in this group, goes through and takes that care of that. Independent errors and zero population errors, these are things we can't test directly within our model. These are more conceptual-based methodological things we need to take care of. Okay, all right. So that was a quick run through assumptions. What we'll finish up with is actually working through an example in the slides, and then we'll finish up with an actual work through example. What I might do is we'll take a look and see how things progress. I think we're doing pretty good in terms of where we are in class. We're not sort of exactly on schedule. How do people feel about those screencasts? I mean, are those nice to work through and sort of see an example and sort of work through kind of on your own? My struggle is whether or not do I spend time with sort of in-class examples and sort of doing this in class, or is it sort of okay? Does it work to do this stuff and say we're going to do is talk about some stuff? Here's an example of how to do it through. In the screencast stuff, right? Because I've gotten feedback both ways. Some people saying, yeah, I like that. Some people saying, well, boy, I wish we would have done that in class so I could ask questions and stuff. What are people's honest sort of opinions, preferences, things like that? Yeah?
I think it's useful to have the condensed resource of the screencast.
Okay.
But it is, I guess this is a non-answer, also conversely helpful for people to ask questions.
Okay, so you value with both of them. Is that kind of where people
we're at.
I think I lean towards in class because I give you a chance to ask questions.
Okay, okay, cool. We're just trying to plan moving forward, because it'll take us a while. We can probably, in the next class, get through the remainder of the slides and then get through sort of the in-class example. Did everybody get the handout? Those up there? Okay, cool. We'll go through, do that then. That'll give us sort of basic stuff, and then that'll give us time to go through, and so we wouldn't start the clock on the next problem set until we're able to work through all of that stuff. But what I'll do is I'll put this first regression set up so you can go through and take a look at it and start playing around with stuff. There are things that you'll be able to do before that don't require you to go through and screen stuff. So if you wanted to go through, get started on that over break, it's totally up to you. You'll be able to do that if you're quarantined somewhere. Sound good? All right, folks, cool.